So up to this point, when we've talked about filtering, we've talked about just a single capacitor in parallel with load. So before we've said filter is just a single capacitor. And so what we're going to look at in this video is how we can improve upon that by having what's called voltage regulators. So our single capacitor is going to work pretty well if we have a small output current. So let's just say this is going to be okay if our current is about 100 milliamps or less. So let's say less than or equal to about 100 milliamps. As we get to larger currents, we'll see that our capacitor size is going to become impractical. And so this is assuming we want a relatively small ripple voltage. So assuming that we can have a ripple, let's say on the order of millivolts. And remember, for some applications, we might not be as concerned with our ripple voltage. Maybe we have a lighting application or heating where we don't really need to rein that in so much. So in order to see why our capacitors aren't practical for these higher current applications, let's consider an example. So let's say we have some 1 amp DC power supply. So 1 amp DC power supply. And so let's say that we've got this, this 1 amp DC power from some AC source. So it's operating from some AC source. And so let's say we're in a country where we have 60 hertz frequency for our AC. And so 60 hertz AC voltage. And in going from this 60 hertz AC voltage to our 1 amp DC, let's say we've used a full wave bridge rectifier. So we've used the full wave bridge rectifier to go from our AC to DC. And so what we want to know is what's the minimum capacitance needed to keep our ripple voltage below a certain point. So let's say what is our minimum capacitance needed, and let's say we want to keep our V ripple below 10 millivolts. So we want V ripple less than 10 millivolts. So this would be a good spot to pause the video and maybe try to work through this by yourself. So, of course, what we can do is we can rearrange the equation we had from our previous video about filtering with a parallel capacitor, or a capacitor in parallel with the load. And so if we just take that equation and rearrange it, we can solve for our capacitance value. So that becomes our capacitance is equal to IDC in our numerator, so that's our DC current at the output of our power supply. And then in the denominator, we now have V ripple being multiplied by our ripple frequency. So something to be very careful of is, note up here, we said that we have used a full wave bridge rectifier to rectify this AC signal into a DC signal. And so if you recall, for our full wave bridge rectifier, our ripple frequency is actually twice our input frequency. So we still have our V ripple and our IDC, but we need to adjust this to be 2 times our input frequency, where our input frequency is going to be the 60 hertz value. So our input is the 60 hertz that we got in from our primary source on our input side of the power supply. So now we can just plug in the values as we have them, and we see that our capacitance, so we have a 1 amp current, that's our DC current. For our ripple voltage, we're saying we want it to be less than 10 millivolts. So let's say we want to be just on that acceptable border, so right at 10 millivolts. So let's say we had less than or equal to. So that would be 0.01 volts, just to put everything sort of in the base units. And then for our frequency, we have 2 times our input frequency, which was 60 hertz. So plugging that in, what we get is 833.3 millifarads. So this is, of course, an extremely large capacitor. This is almost 1 farad capacitance. And so as you might remember from some of our previous work in the lab, typical capacitances for this type of scale of electronic circuit are on the order of microamps, nanoamps, or even sometimes smaller than that into the pico, or sorry, not amps, farads. So microfarads, nanofarads, or sometimes even into picofarad range. And so those are, of course, 10 to the minus 6, 10 to the minus 9 for nano, and 10 to the minus 12 for pico. So this would be micro, nano, and pico. And so what we see here, that this is almost on the order of 1 farad, so 10 to the 0. So it's much larger than what we would normally deal with. So a follow-up question we could ask then is, what if we use a half-wave rectifier instead? So what if a half-wave rectifier is used instead? Is that going to affect the size of the capacitor we need? So again, a good opportunity to pause the video and consider this problem for yourself for a second. And so, of course, the answer is that yes, this is going to affect it, because remember, for our half-wave rectifier, our ripple frequency is equal to our input frequency. And so essentially we're not going to have this factor of 2 in the denominator, and so that means that our capacitor is essentially going to be doubled from what we had for our full-wave rectifier. So if we have a half-wave rectifier and the same condition of 1 amp output, and we want our ripple below 10 millivolts, and we have 60 hertz signal coming in, then our capacitance would need to be approximately 1.6 farad. So again, this is a very, very large capacitance. So this is impractically large for the types of circuits that we're looking at. So instead of doing this sort of brute force with our parallel capacitor, what we're going to look at instead is our voltage regulators. So instead of brute force with our capacitors, we want to look at our voltage regulators as a way to sort of make this a little more practical, so we don't have to have these huge bulky capacitors everywhere. And of course, once we get so high, it actually becomes very costly to make capacitors that size, let alone to find the space to fit them into the circuit. So a couple notes about our voltage regulators then. So if we're talking about our voltage regulators here, just copy that down. So our voltage regulators, a couple key properties as far as what they're doing. So our voltage regulators are going to be converting a DC voltage to another DC voltage. So we're doing DC to DC conversion. And so what we're going to be looking at again is voltage. So let me just put voltage here. And so we're actually going to see different types. So you notice in the notes it says to a lower voltage, but we're actually going to be looking at different types of regulators. For certain types it is to a lower voltage, but for other types it can step it up to a higher voltage as well. And so typically this is going to be, our voltage regulators are going to be improving both our line and load regulation. So typically we're improving our D line and our D load. And so if we think back to where we defined those in a previous video, what this means is that as that input frequency or that input AC power, well, in this case our DC power is changing, or as our load is changing, our final output is not going to be as sensitive to those changes. Okay, so before we get into the various types of voltage regulators, or the specific types I should say, let's talk about the two broad types that we're going to discuss in this class. So of our two broad types, we have one, which is our linear voltage regulator. And so we'll see this in the form of a series pass regulator. And so what we're going to see with these linear voltage regulators is they're not as good in terms of efficiency, because they're having to basically dissipate any power difference between the input and output in some device that is connected in series between the input and output. So the solution to make things more efficient is to employ something called a switching power supply. And so with our switching power supply, we can essentially think of it as creating a pulse width modulated signal where our output is going to be the average of what gets through our switching. So unlike the previous type, this is of course going to be nonlinear, but it's going to have a better efficiency. So of course that is the draw of that. Okay, so before we get into another video detailing these, just one other quick note about this linear voltage regulator is typically the key component is going to be the voltage reference. So a key component of this type 1 is some type of voltage reference. And typically what this voltage reference is going to be is a Zener diode. And so usually this Zener diode is going to be operated in the reverse bias region, specifically in the breakdown region. So if you recall from analog devices what our IV curve looks like for a Zener diode, so here we have our diode current, and here we have our diode voltage. So let me just change over to blue here. So we have a standard sort of forward curve where we get into this exponential increase as our voltage is increasing. And then as we go below 0, we have, and let me sort of make that a little smaller, we have ideally a very small current. And then once we reach breakdown for our Zener diode, sort of the unique thing about that is this voltage is staying relatively constant. And so the idea is that as we move up or down on this line, so maybe we start here, and for whatever reason our current is being increased through this diode, so maybe it comes over to 0.2, and then maybe the current decreases and it comes back to 0.3. And so what we see for all of these points here, they're roughly corresponding to the same breakdown voltage for our Zener diode, which we can label as negative VZ. And so the value of this negative VZ, or if we just talk about VZ, our VZ can range anywhere from the order of 4 volts up to 100 volts or higher. So we have a lot of versatility here. And essentially the way this linear voltage regulator is working is it's using this voltage across the Zener diode as a reference to compare to what the output should be. And so what we're going to see in the next video is what we essentially create is a feedback circuit where we're taking a scaled version of the output and we're comparing it to that Zener voltage, and then from there we can make adjustments. So let me just write this out. So we're taking a scaled version of V out, and we're comparing to our reference, which is our Zener diode voltage. And so what we're going to do in the remainder of the videos for this power supply section is to go through and look at specific types of these voltage regulators, both our linear voltage regulator and our switching power supplies.